All right, good evening, ladies and gentlemen. This is Mr. Goodfellow, and I drew the short straw this time around, and I'm going to end up doing all of your vector videos for the entire unit for 6.6 and 6.7. So, golf clap for G. All right, here we go. Ultimately, right here at the beginning, they do give you some review questions for you to take a look at the beginning. And these review questions are actually placed in a really good spot, and they're specifically designed to help you understand what kind of stuff we're going to be talking about in the future for 6.6 and 6.7, which is going to be about vectors. So at this point in time in the video, I'd prefer you to actually pause it. And I'm going to give a few seconds for while you pause it. Try these problems out, and then we can discuss what each one of them is about and how they're going to pertain to where we're headed in this next couple of units. And poof, here's some of the answers that you could have come up with out of the actual review. Now, each one of these I'll talk about because they definitely have an impact of what we're going to be seeing in this next part of the unit, okay? First off, changing something like r equals 2 secant of theta into rectangular, we're going to use the reciprocal method by writing the 2 over cosine. And once we do so, we can cross multiply and we get this r cosine theta is equal to 2, and r cosine, seen it in the past when we did polar, turned out to be x. Now, I'm going to pause right here for just a second and just say this r cosine concept right here that you learned during the polar unit, extremely important when we start talking about vectors. So that part's going to come back. Those formulas are going to come back. Number 2, trying to write the complex rectangular coordinate, what two formulas would you need to be able to change it? Well, you would definitely need the r equals x squared plus y squared and square rooted idea to get its radius, and you would need the theta is equal to the inverse tangent of b over a to get the angle, and those two formulas again are going to come back in vectors as well. Vectors and polar really mesh well together. They're basically the same kinds of ideas. And then the last one, number 3, changing something from rectangular to polar, I'm employing those two formulas that I stated up above, taking a look at where that coordinate is, which is in the second, and I should have put second here and not third quadrant, sorry about that. Keep in mind that the inverse tangent only gives you answers in the first and the fourth, and you would need to add pi to it if you were going to go into the second quadrant. Now, everything that you're seeing right there was really what you ended up doing and pertaining when it came to polar. And vectors is just like polar. It's a very similar concept. Now, what the heck is a vector? Well, and your question is pertinent to say, what are they or who are they? And I have a little YouTube link right here, which I'm going to show you an explanation of what a vector is. Now, you have to actually picture a math teacher sitting in a movie theater watching for the first time this amazing movie, which you guys well know is Despicable Me. And the villain in this particular movie happens to have a mathematical name. Here he is.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude.
Oh, yeah! Okay, you gotta get excited about that. The key here is his name actually means a mathematical term, and it fits for what he's trying to get through. It's a mathematical term that is, oh, there's a good place to stop.
With both direction and magnitude. Oh, yeah!
Hey, you gotta celebrate that. That's totally awesome. Okay, so key thing to remember that we're talking about here is that a vector is exactly what he explained there. It is a quantity or represented by an arrow. So it's an arrow concept, and that quantity has two basic things going on to it. It has a directional component, which we would think of in terms of theta, and it also has a size of the actual arrow, which is an idea about magnitude. Or we'll think about magnitude as kind of an idea like R. R, or radiuses, were very similar to magnitude kinds of concepts. So a vector, its direct definition, is a representation of a directed line segment. Now, if I say directed line segment, I mean a ray, because it has a specific direction that it's going in, with a specific direction, theta, and a specific magnitude, or R kind of concept, okay? We're going to talk about a certain size or a certain amount of force that it's talking about. Now, in trig, vectors can actually be represented as an ordered pair. Now, this is the part that can kind of be a little confusing. You're like, it's an ordered pair? Well, that ordered pair has its terminal side, meaning one end of the ray starts at 0, 0. So we really like to draw our vectors starting from 0, 0. This is where the ray starts, and then it directionally points in another place. Now, if we put it in this particular kind of scenario, we refer to it as being in standard position. And then we can note where that location is right up there by a notation method that represents where it's going to be at. If the first end is at 0, 0, hey, maybe that end is at 3 and 4. Now, an old notation for this is to actually use, instead of soft brackets, is to use pointed brackets. And that would really denote that you were talking about a vector. Okay? Other ways to explain it would be to kind of explain it in a complex kind of looking way. And that means that there is a horizontal component and a vertical component that actually make it. So how much do you go over, right and left, and how much do you go up and down would be the ideas here. We refer to this as the I and J format, is the way that it is. And when we talk about vectors in general, when we're talking about, say, naming a specific vector, we give them specific italicized names with an arrow over the top, meaning that we're talking about a vector. So like vector W, I would put an arrow over the top of it. And this would mean I'm talking about a vector, okay? Now, vectors are used very often in certain kinds of sciences. Specifically, we use them in physics a ton, because we like to try to explain how objects move. And objects don't move unless they have a direction and a magnitude. So very often we think about things like velocity vectors. You're riding on a roller coaster. Your body is experiencing force in specific directions and specific magnitudes, or force vectors. Same kind of idea. See this guy pushing an actual crate up an inclined plane. That's a force being pushed up that way, and he's a force that he's working against on the inclined plane called friction that's pushing against it, okay? Another one could be like unit vectors or resultant vectors, very similar to what you'd see on a contour wind map. Now that picture doesn't do it very good justice. There, I have another one here that kind of shows you a contour wind field. This right here is a really good representation of wind velocity vectors showing active currents on the actual globe of the Earth. Each one of those little tiny lines that you're seeing right there represents a specific magnitude. Check them out. They represent a specific magnitude and a specific direction. These kinds of ideas can represent things like airflow, how water actually flows, many kinds of forces that you would see in nature can be reflected over a vector notation. Now, how do you actually go about, in example number 1 here, how do you actually draw a vector in its position? So they're saying, hey, I've got this vector v, and I want you to draw it with its terminal side or its ending side at 3 and 4. So you can kind of think of it like it's a coordinate, but the vector is being drawn from standard position. It's going to get stuck at its one starting point at the origin, and then you would go 3 units in a horizontal fashion and 4 units in a vertical fashion to draw a point where that vector is being pointed towards. That would be what the vector would look like. Now, that actual component vector way of writing it would also be equivalent to saying 3i plus 4j. It's just 2 different ways to write the actual component. We usually refer to the x-axis as I and the y-axis as j. Don't ask me why they're I and j. They just are because that's the way we think about them in vectors, okay? Now, how would you come up with this vector's individual direction? And direction would ultimately be about finding its theta. Now, theta is easy to find. We found stuff like this when we did polar. We were talking about that being a possible polar point. And that would be by taking the inverse tangent of its y over x, or I'm going to say not just y, but I'm going to say it's b over a. That's the same thing. We talk about its b amount and its a, or its a amount and its b amount. That's the same thing as x and y, or y and x. So what would I do here? I'd take the inverse tangent of 2 different numbers, which is 4 over 3, and I'd plug that in my calculator and solve. Now, vectors are very commonly denoted in degrees. So usually you will have your calculator in a degree mode when you do this. And it would be the inverse tangent. And I've got to make sure that when I'm doing this, I'm thinking about what quadrant it actually turns out to be in. And this would be a 53.1 degree angle in the first quadrant. And that coincides with my picture in the first quadrant. Now, one of the things you're going to get very, very good at when you do vectors is, number 1, you're going to need to draw a picture. Okay? Pictures are totally key in being able to write and do vectors in general. So first off, I've got its direction. Second, I would want to find its magnitude. Now, when we talked about it in polar, we called that idea the radius, which makes sense, or it's the hypotenuse, because ultimately it is nothing more than a horizontal and vertical component of a right triangle is really what's going on. So it's technically a hypotenuse is really what it is, or you could think of it as an R, but we call it, when we talk about in a vector, we call it a magnitude. And when we write magnitude concepts, we use double bars around it saying, hey, vector v is the one I want you to talk about, and I want you to go find its magnitude, and finding that hypotenuse would be found by taking the square root of a squared plus b squared. So these 2 formulas right here are going to be the fundamentals to being able to do good in vectors. That answer would be the square root of 4 squared plus 3 squared, and that'd be 16 added to 9, and the square root of that would be the number 5. So you would be able to say that the magnitude of that vector is 5 whatever it is, 5 newtons, 5 miles per hour, 5 kilopascals, whatever the unit was, but it is going in a direction of 53.1 degrees, okay? Now, if you think about or vectors like that, you could actually break a specific vector up into individual units that are going out along there. And if you were going to say that vector had a vector length of 5, you'd be like, oh, how could I represent it? Well, I could chunk it up into 5 individual equal parts, and I could write the vector of 3, 4 as a unit vector. Now, all you end up doing is taking the original vector, which is 3i plus 4j, written in its ij combos, and you just take it and divide it by the magnitude underneath. So this right here, what I'm drawing, would be referred to as the unit vector. And the unit vector just represents the smallest unit, singular unit, of that vector based on that vector's position and its magnitude. So you just take the position of the vector and divide by its magnitude. Pretty straightforward if you're thinking about it, okay? Now, vectors can easily be done, as I was doing right here. I'm going to put the position right here, is it's in standard position, and it's 3 units, 1, 2, 3 over, and 1, 2, 3, 4 up, like that. This would be the location. 1, 2, 3, I think I got that in the right spot. This would be the position of the vector of it in standard position. And we usually denote them with an arrow because they are directional forces going in a specific place. Now, if you want to write it as a sum of its individual vectors, I've already done that. We just break it down into how much was it moved horizontally, how much was it moved vertically, and that would be 3 in the I direction, and then positive 4 in the j direction if you were going in the j component. Now keep in mind, if you're going in the I way, I concept, you're basically talking positive is to the right and negative is to the left. Keep this in mind, that's important. And j would mean that if you're going positive, you're going up, and negative means you're going down, okay? Now, we're going to use that concept and think about direction and magnitude questions here in example number 2. It says, could you write a vector that goes in the exact same direction as 4i and minus 4j? Now, I'm going to look at this guy right here, and I'm going to say, where the heck is 4i minus 4j? Well, that means it's in standard position. Here's where it's going to be connected to, and I would go 4 units in the I direction and negative 4 units in the j direction, and that particular vector would be pointing down there. Now, what I want to do is find one that's going in exactly the same direction, but doesn't have the same size. And if I was going to do that, I'd have to stick along this line, but maybe make the actual vector smaller. So one that's going in the same direction, but not in the same, is not the same magnitude, would maybe be 2i minus 2j. That's still going down into the 4th quadrant, and it's still going along the exact same direction. You get the idea? Now, let's continue to try a couple of these other ones. Could you write a vector that has the same magnitude as 4i and 4j? So again, I'm going to go back to that 4i, 4j concept, and I want one that's going in that has the same size or magnitude to that. Well, I could pick a vector that's going in a completely different direction, but it's going in the same amount of magnitude. So maybe an answer could be 4i plus 4j. It may be in the 1st quadrant, but it still has exactly the same magnitude because 4 squared plus 4 squared still boils down to the same square root, regardless if it was positive or negative. What if you wanted to make a vector that had the opposite direction? Well, if this one is going in this direction at that, I would pick one that went in the opposite direction. That could be written as negative 4i plus 4j. It would still have the same magnitude, but it'd be going in an opposing direction. So knowing what you're talking about when you're talking about horizontal and vertical components can be very important, okay? Now, those vertical and horizontal components are great, especially when they're drawn from standard position. What if you have a vector stated like this, that you're going from A to B, but you are not stuck at standard position? And you are like, oh man, I wish it was right here, but it's been put at 2 and 3 is where it's starting from. 1, 2, 1, 2, 3 is where it's starting from. That's point A. And then 4 and 7, 3, 4, 4, 5, 6, 7. Here's point B up here, and I want to draw this vector in this position. Well, how could I represent that vector as a set of terms of horizontal and vertical components? Well, it's exactly like it says that it is. If you wanted to talk about its I component, you would move it over this amount, which would be a difference between 2 and 4, or 2i, because you're going right. Now, if I wanted to talk about its horizontal component, I'd be going up, and that would be the difference between 3 and 7, which is 4, and that'd be 4j. Now, this particular vector has the exact same components. If I drew it from here, 2 over and 4 up, this vector is exactly the same size and the same direction, but drawn from standard position. Now, if I wanted to find the magnitude of that vector, I would find the answer as the magnitude of vector v would be the square root of 2 squared plus 4 squared, and that answer would be 4 plus 16, or the square root of 20, or better yet, 2 root 5 would be the magnitude of that. And you could find its direction by doing the inverse tangent, and I'm just going to set that guy up as doing the inverse tangent of the y component over the x component, or 4 divided by 2, and you take the inverse tan. All right? Now, notice these same functions right here and right here, they are going to be the fundamental keys to being able to get vector magnitudes and directions. So think about what kind of simple operations could you perform on 2 points to translate those vectors to their initial points. Well, what you want to do is find their horizontal component, and find out whether or not if it's positive because it's going right, or if it's negative because it's going left. And it's really about finding a difference between the two x values is really what you're doing. If I wanted to do the other part, I'd do the vertical component of the deal, positive being not right, but positive being up, and negative being down. Okay, and again, this would be the difference of the y's. Okay, it's really about looking at those other two components to figure out what's going on. Okay, now math people love, as I've always told them, we love closure. And closure basically means that if I have this new idea called vectors, or a new idea like polar, or rectangular complex, or fractions, or whatever it is, then the key to understanding math is to make sure that the operators work. Okay? And operators are extremely important, like addition and subtraction and multiplication and division and such down the line. Okay? It actually turns out that vectors only have a couple of operators that work on them. Addition and subtraction are primarily the most important vector operators that you need to understand. Multiplication, in the sense that you're used to, does not exist. Neither does division. Okay? Their powers don't work and those kinds of ideas. Now, addition and subtraction is going to be your first key concepts. When you add or subtract positional vectors, the cool part about adding and subtracting vectors is all you do is you add and subtract the components. So if I had something, we'll do one that's down here. Let's do, let's just do like v plus w that's listed down there. All you would do is combine the like component ideas. That would be 7i listed right here, and negative 2j, and that, well, that's plus 3j. And that's how simple it really is. Okay? Be careful of subtraction. When you do subtraction, you want to think of distributing the negative through the whole entire right-hand vector and then adding your components. Okay? Now, another kind of multiplication that's out there, it's not true multiplication, it's called scalar multiplication. And all that one is it's a distributive multiplication. It's like you put a scalar number on the outside and you distribute it on the actual vector. Okay, now we're going to see each one of those kinds of ideas. This one says do 3v plus 2u. Now these 3's and 2's that are in the front, these are what are called scalar multipliers. And it just means take the scalar multiplier of v and actually triple everything, which is taking the vector and really increasing its size, or better yet, its magnitude. So you're really adding 9i is being 9i plus minus 6j is really being added to, the 2 is being doubled on the u, negative 4i, and negative 12j. And you would add like components here, and the actual new vector would be 5i and negative 18j. Pretty straightforward adding vectors concept. Watch for your scalars. Scalars are taken care of first, so there's kind of a PEMDAS here. So you take care of your scalar before you would do the addition or subtraction. I think that kind of makes sense. 4v is really 12i minus 8j, and I want to subtract the entire vector w from it. So notice I'm using parentheses here. So to ensure that I see there's got to be a sign change here, that I am really changing this vector and subtracting it. Now I can combine my like terms just like in addition. 12i and that would be equal to 8i, and negative 8j and negative 5j would be negative 13j. And if you write them with a plus in between and a subtraction, that's totally fine. You could write it as minus. That's okay too as well. It's just an expression of horizontal and vertical components. This is basically saying the vector is going right, and this is saying the vector is going down. So start thinking that way. It's really a component concept. Now, this one is basically telling you find the subtraction first and then find the magnitude of that vector that you came up with. So what's the magnitude of u minus w? So let's see, u minus w is negative 2i minus 6j minus the entire vector of w, which is 4i plus 4j, and then find the magnitude of that. Well, I'm going to take care of this subtraction sign by getting all the right components there. And then I'm going to say, what's the magnitude of negative 6i and negative 11j? Check my work there, make sure I did it right. And then if I wanted that magnitude, the magnitude is just a scalar answer. It's about how much force is being taken care of there. And I would use the square root of x squared plus y squared, or a squared plus b squared, same difference, Pythagorean theorem, negative 6 quantity squared plus negative 11 quantity squared, and I'd get 36 plus 121 and take the square root of that. And that's 157, I think. You guys check my math there. That seems right. And I'd have to go to my good old Bethany to figure out what I'd get there. The square root of 157. And it's very common for magnitudes to be decimal equivalents. Let's do 2 decimal places here, 12.53. And I don't know what that unit is on it. It's unitless at this point in time, but it is a scalar number representing how much magnitude or hypotenuse is in that vector. Okay? All right, I hope that gave you some ideas about what vectors are and gives you a good start on your 6-6 assignment, which will be a Math Excel assignment. All right? Keep in mind that vectors are all about direction and magnitude. Oh yeah!